All right. Well, good afternoon, everyone. Welcome to another IFAS AI and Data Science seminar. Our speaker today is Dr. Yunjun Xu. He's a professor in the Department of Mechanical and Aerospace Engineering at UCF. He got his PhD from the University of Florida. His research is in the general area of guidance, navigation, and control and robotics. In the recent decade, his research team is heavily involved in developing robotic-related technologies for specialty crops. He's currently leading an IFAS-sponsored expanding AI project, and he's an AI Associate Fellow and an ASME Fellow. So please welcome Dr. Xu.
Thanks so much for the invitation, and I think Dr. Lee talked to me last year. I'm glad to see actually many of my friends or colleagues also in the audience today. Today I'm going to talk robotic and control related stuff, we're developing the lab. Some are joint developed with my colleagues or friends, for example, Dr. Ajihara, and a few other at the UF. So I'm currently at the UCF, Mechanical and Aerospace Engineering. The past probably 10, 12 years, I have been heavily involved in developing different kind of robotic platforms and control algorithms for field robots working strawberry field particularly. So in today's talk, I'll give this outline. I'll talk about the introduction and motivation, and I have a few slides talking about our current, UCF expanding AI program. Only a few minutes. Then I will dive into field robot motion control, harvesting, scheduling, detecting disease, and some mechanism we develop here. The algorithms we develop here have mostly in control theory side. Our current work have a little bit AI, but not much in today's talk. So a little bit background. Everyone knows that we are short of labor. Also, the farmers typically they are aging right now, and the young generation workers they are not interested in or motivated to be working in the agriculture field. Partially because not very high salary compared with other engineering job, or maybe they have a little bit different perspective as a career. Also, from the whole worldwide, urbanization leads to population decrease in rural areas, so farmer numbers decrease as well. And also, the working in the field is very physically demanding, and sometimes you're exposed to chemicals and other things. So for the past maybe 2 or 3 decades, robotic technology have been attracting much attention, and many technologies has been developed, try to reduce labor dependence, which are time consuming, labor intensive, and physically demanding. Okay. Also, recent decades, federal agencies such as NSF and NIFA has invested a lot of money and sponsored many projects in this area. And I know that the UF and UCF all has secure a pretty big chunk of funding to hire more people in robotics and specifically AI. In our lab, these slides show you what kind of stuff we do in the ARC lab, which is my lab at the UCF. We are pretty heavy in control theory. We do optimal control, constrained or non-constrained. We do server visual algorithm development. Also, we develop robust adaptive control for robotic stuff. And from the cooperative level, we design scheduling algorithms. We do corporate planning, corporate path planning algorithms. And we do video image processing, developing different kind of filters, estimation algorithms. And we also working previously, not recently, we do data association techniques for robotic stuff. In terms of hardware, we occasionally build sensors. We build anti-effectors, which I'll show you some of them in today's talk later on. And in terms of dynamics, we do thermomechanics, we do dynamic modeling for vehicle systems. Also, we do inverse kinematic stuff. So we program a software. We do software architecture design. We do software development. We pick hardware. We do sensor actuator integrations. And for the past maybe 4 or 5 years, we also slowly introduce AI methods into our controller and navigation estimation tasks in the robotic or field robots. Also, we we conduct lots of field tests. Typically, in the strawberry season, we go to field probably once a week, sometimes twice a week. We used to have a strawberry field nearby UCF, but since last year, maybe earlier, I think last December, November time, they closed their business. So now we have to go to a field which is about 1 hour away from us. Also, we did some like sensor and test in Gulf Coast with help from Dr. Sensuki. So we'll show some ideas of the field test in this presentation as well. Okay, so that's basically a brief introduction of the motivation and what we're doing in the lab. The next, we'll talk a little bit about our UCF expanding AI program. As many of you know that we have, I think we have about 6 NIFA-funded AI institutes. Start like 3 or 4 years ago, and a couple of years ago they start have an expanding AI program, and we got funded about 1.5 years ago. Okay, we are collaborating with AGAID, which is AGAID. The leading institute was actually is Washington State University. So at the UCF part, I'm the PI, and I'm working on GNCs and scheduling using AI methods, mostly reinforcement learning stuff. And Dr. Belloni, he's a professor at the UCF computer science. He's using AI like end-to-end learning stuff for robotic manipulations. Hopefully can help, picking and other things in agricultural operations. Dr. Chen, he's expert in computer vision. He's tried to use his foundational model to help remote sensing and other things. And I think many of you know Dr. Manoj Kaki. He's now at Cornell. He's our liaison with AGAID, help us build a connection with them. So hopefully, in maybe a very short time, we can implement the algorithms we developed at the UCF and to help problems in the center they may have. And Dr. Central, I think many of you also know, he's also a UF alumni. He's working on pesticides residue analysis using computer vision technology. Okay, so those are 5 main people in this center. We are trying to, through this funded center, we try to develop new AI technologies for urgent issues in agriculture industry. We try to engage or involve more and more researchers or faculties, students into the agriculture research problems. As you probably all know, UCF is pretty big university. We have, for example, our department have a huge number of enrollment of students. Also, we have lots of faculty, doing different kind of research. But so far at UCF, we don't have many heavily involved in agriculture-related research. So through this program, our goal is to try to inspire more and more people, develop methods which potentially can help agricultural, issues or problems we have. And we have our expanding AI partnership program has 5 research things or topics. They are motion control, scheduling, sensing, manipulation, and residue analysis. Okay. We also have many different kind of activities. For example, we have some exchange program. We send students to either Washington State or Cornell probably this year, and sometimes they send students to us, so we can have students to collaborate. Also, we use our UCF Campus Connect program to involve some high school students, get them interested in doing engineering work. And also, this picture shows the work done by a summer intern in our computer vision IU program. We typically propose a problem to them, then they recruit students working on the project. Okay. So we have lots of activities in this partnership program, and we have a website. If you're interested in, you can always go to our website and find out what we are doing there. Okay. This slide is provided by Dr. Centra. I'm not expert in residual stuff, so he probably know much better. If you have any questions related to how to do residual analysis using computer vision, feel free to let me know. I will connect you guys together and you guys can discuss. So basically what he planned to do is choose the AI methods to utilize AI methods to analyze pesticide content through the visual residues found on leaves after the pesticides being applied. He published a paper, I think the end of last year. In that paper, he used mask RCNN module to predict the residues happen there. So as I said, if you are interested in, I will be very happy to connect you and Dr. Central, so you can discuss more. I think he has been using different kind of pesticides for citrus greening problems for the past, I'll say 10 years minimum. I remember he started his work around 2014 or 2015 timeframe. Okay, so I just give you a little bit brief introduction of what we have done in my lab. Also, what happened at UCF expanding AI program. So the next few things I want to discuss a little bit more detail about how we control the robot, how we design robot, all kinds of estimation control algorithms we have been working on. So first is our field robot. Field robot is in a pretty, I'll say it's pretty good needs from many different operations in order to saving labor, right? For example, in phenotyping, I know that several faculties at UF, they have their own robotic platform developed in recent years for phenotyping, like Dr. Lee. It also can be used for harvesting. We developed one here since 2012. So our harvester have been here for roughly a decade. Also, people develop or purchase, robotic platform for irrigation purpose, for disease detection, and for applying pesticides, and many, many others. Okay, people use UAVs, drones. We used before as well. Also, people use ground robot. And today's presentation, I'll be focused mainly on ground robotic stuff. From our dynamics and control perspective, they have lots of challenges being brought by the farm conditions to our robotic design and control. For example, weather condition. It can rain, it may have big wind, and those things may be okay. You can cover them and may be fine. But I think the light condition is very crucial because many our sensor is vision-based. Okay? So light condition can causing distractions or errors in our estimation and navigation. Sensor measurements have uncertainties and noise like GPS, LiDAR, camera, ultrasonic sensors, and gyroscopes. They all have noise and uncertainties we have to address in our controller design. And different farm geometry layouts causing some issues. I remember initially our robotic platform, is one size. So I think around 2015, 2016 timeframe, we make a little bit change on our robotic platform so that right now we basically put several holes there, put different pins in different location. So it depends on the farm geometry, we can do some minor adjustment. So make sure our robot can go through the rows. Another challenging issue in Florida is the field sometimes have lots of sand there, causing big problem. I'll show you a video, you will know what I'm talking about. Okay, the sandy terrain causing some issues. I know several good like commercial farms. They are pretty, terrain or sand is not so bad. They are pretty compact. But we have been testing robot in several fields which are very sandy terrain, causing issues to our motion control of the robot. So those are the challenges in GNC. It have very noisy measurements, especially if you don't buy very expensive sensor. The low cost sensor like $100, $200 sensor are very noisy, okay, in terms of measurement. Uneven terrain or very loose sandy terrain in Florida causing problems. Different light conditions or distract your vision-based approach, which I'll mention a little bit in one experiment we seeing that. These are just the typical, our vehicle dynamics model. You have state functions and output functions. Okay, sometimes output function can be used as a measurement model function. So let me show you one video. I'll disable the sound. The video is very slow, but I'll probably move to the middle. This video was took a couple weeks ago when we conduct the experiment in a strawberry field. You see the robot is moving out of the row, and then now it go to the very loose sandy terrain. You can see it tried to automatically find the next row and go there, and it was stuck somewhere. You can hear the noise. And the robot tried to turn and find the minimum time or minimum pass, go to the next row. And it was stuck here. Then my student Louis, he found that actually stuck there. The computer generated command, but the wheel is stuck in the sand, so he has to push a little bit. And to the end, when the robot tried to turn and find the right angle to enter to the next row, also because the very loose sand, the wheel kind of slipped and almost hit the row. So Mark has to quickly go there, pull the cable out, so it will not damage the row. Typically, if you damage row, the row will not be happy with you. Okay. So that's the video I want to show you. So in terms of modeling part, accurate model may not be always available. Sometimes the model can be pretty complex, including terrain and wheel interactions, because it's not like concrete surface. Even when your robot go over the row, which looks like try to stick to a straight line, you have to control it very precisely, because the wheel, the width of the wheel, or the distance between rows, they are pretty narrow. Okay, so you have to control it very well. It's not a simple like zigzag type, line follow algorithm will work. You have to be very careful. You put in lots of logic loop, different kind of PID loop to make sure your robot will not scratch the plastic cover. Okay, so that's basically the issues and challenges we see if you try to develop autonomous field robots in strawberry field like this one. Let's see. So first, controller I'm going to show today is vision-based nonlinear robust control. This was done, I think 2014 or maybe 2015, I forget. So what we are doing is we propose a three-phase controller. We derived, a very simple uncertainty bound to capture the uncertainty coming from your camera focal length. Because sometimes the camera focal length may not be accurate, so we try to make sure we know the uncertainty bounds on it. And we prove the stability and robustness with respect to this kind of bounded uncertainty, right? Then so we have a guaranteed asymptotic stability. It's pretty mathematical equation, so I don't show all of them here. We separate the motion control for a row head transient control, basically from one row to the next one. into three phases. One is basically you go straight line like this one, two here. Then you do a roughly 90-degree turn, go to 3.18 section, then start from 3.1b to 2 and 3.2. This part will be controlled by your camera. The camera will try to detect the center line of the row according to the color difference and try to align well with next row. Okay, so this will be the picture we draw here, and let me see how can we move this away. Cannot move this way, so I cannot see the picture myself. So we have the left picture here, figure 3, show you how we handle the overbed motion, meaning that your robot is already over the row and you can start to picking and other things or do disease detection. By the way, at that time, this robot was built for disease detection. I collaborate with Dr. Reza Isani. That time he was at the UF. We have a project from NIFA. Once the robot receive coordinate from the UAV, which do a rapid scanning of the field, this robot will go there to do detailed detection. So this robot have a overbed motion, and this controller developed for the crossbed, we call crossbed, or call row transition control. Okay, so it's purely vision based. And that time we didn't use GPS or something because one, that time 2013, 2014, RTK GPS is still pretty expensive. Also because very highly accurate. We prefer not to use it for a certain reason, and we purely used camera only. So this will be the video show you how this three-phase controller really works. The student combine lots of video together. Sorry. Oh, sorry again. I keep clicking one button. So I'll move a little bit forward, fast forward. You can see how it do the overbed and crossbed. And this controller is not optimal controller. It's just robust controller. Have one or two sections which is open loop control, have no stability guarantee. From 3.B to 3.2, this have stability guarantee because we do get feedback and we try to follow a center line. Move a little bit quicker so I can show you more stuff later on. You can see the robot moves pretty slow. The maximum capacity of the robot currently setting is 20 centimeter per second. Also, we have lots of pause command in our software, so we intentionally slow down when you do crossbed, overbed stuff. But in reality, if you really want to make it work in the field, we can remove all this, pause command, so it will run a little bit faster. Here the video shows it's pretty slow. Okay, so I just show you which is a non-robust control, vision-based, which is not optimal. So the next controller we developed is try to address the optimal perspective. We try to use develop a controller which can achieve a minimum time transition from row to row. So in this project was funded by NSF 2019 that time, and we developed some kind of little bit AI flavored controller we call adaptive dynamic programming approach. I try to achieve a minimum. We developed this adaptive programming problem using our subspace manifold approach, which means that the search space for optimization is reduced significantly, following certain motion manifold we developed. Since it's a subspace optimal control methods, we cannot guarantee it's a perfect optimal, but we can guarantee our controller is better than certain baseline controller, right? So we develop some lower bounds for optimality. In this controller, we use adaptive law to handle two uncertainties. One is ground condition factor, another one is decomposition factor. Both of them used to solve skid issue or a slip issue, with sandy terrain. We also have constraints on control, and we have state constraints in the field of view of the camera. So this is a picture of the robot you can see, and we put the April tag on the roll head. So the camera on board will try to find out the distance and orientation with respect to this April tag. The April tag software, I think we follow the package from University of Michigan. The good things about this controller is that we project our robot position and orientation into the camera's focal plane. So it sounds like our controller will track the pixel instead of the actual world coordinate in the field. And later on became a one-direction search. It's really fast and achieve a certain level of optimality in our trajectory or control, motion control. It's pretty mathematic as well. So the picture probably too small. This shows piece of the equations in our adaptive dynamic programming algorithm. So this will be the software we developed. We have robot attitude or pose estimation. We have inverse dynamics policy in our reinforcement in our adaptive dynamic programming part. Then we have through that we find our control a crossback controller or roll transition controller. And we have a visual marker, which is April tag here. We adaptively tuning the decomposition factor and the ground condition factor, which is related to the terrain and vehicle interaction between the robot and the sand condition. Here's a video show you how the student did he combined many experiments together. The previous slides I showed a nonlinear robust controller. We've done probably 100 times experimental success rate is about 80% without scratching, the bed, align well. For this optimal controller we did, our success rate is 100% because every time it can correctly find the next row and align very well with the next row. Not like the first video I show you, student have to pull the plug away, otherwise the robot will hit the roll and damage the plastic cover on it. And operating the robot currently needs one student, but we needed two students to transport robot from the lab to the field. I think this video shows that. Oh, by the way, in this vision-based roll transition control, we automatically adjust the exposure rate of the camera according to the sunlight of that particular time. So once the robot coming into the roll, then the controller will switch from this optimal control back to the PID control for overbed portion. Overbed portion is pretty stable right now, but compared with overbed part, roll transition is always more challenging. That's the reason the past almost 7-8 years we are focused heavily on the roll transition control instead of the overbed part. I'll move quicker so it will actually he just showed comparison controller from the previous student. And this shows you how they quickly disassemble everything and move everything back to the lab. The reason we have to every time put it back, assembly and integrate assembly and all disassembly is because the lab door is a little bit narrow compared with the robot itself. So we will have to take parts off and then move out of the lab, then then move to the truck and then ship to the transport to the field, then put them back. So every time when we finish our experiment, we also have to disassemble them, then go to lab and put them together. Okay. So basically, that's the two type of controller we developed for a motion control. One is robust control, one is our optimal control methods. I haven't showed the slides. We did we did apply AI methods since last year. We use our own optimal control in a reinforcement learning framework. We are still working on it, and it tests pretty well in the simulation, but we haven't been able to implement in hardware yet. So that's basically how we do our motion control for the robot. And the next thing I'm going to spend like maybe 2-3 minutes talk about is our role allocation stuff. This was also a project from same project with the previous one, but one research task is to how to schedule, how to allocate robot to different roles. Since nowadays more and more robotic stuff has been introduced to agriculture field. And I think one day, this scheduling will become important in order to improve efficiency and help of growers to increase their profit margin. Okay, so this is a picture we show also for the strawberry field. This is some kind of picture I put together before. If we have multiple strawberry robot together, if one robot is kind of go to the end of the row, what he going to do, right? You go to neighboring row to pick strawberry, or maybe go to a row which is far away from the current row. So we developed something called a tri-layer auction-based decentralized row allocation algorithm. About around 2018 or 2017 time. We implemented in our simulation software, and also we build a wireless communication between them. We're testing Monte Carlo simulation, but we haven't been testing hardware because we only have 2 robots in the lab right now. In order to test scheduling stuff, you probably need to have like 5 or 6 because 2 robot scheduling is too simple. Our lab have 2 right now. We anticipate to build probably a 3rd one later this year. This is the GUI we developed, so you can kind of see, when a robot go to the end, this algorithm will find out which role this robot should go to, either helping the neighboring robot or go to a role which is far away from your current role. This scheduling algorithm is decentralized, but not fully decentralized because we have 3 layers. The last layer is basically saying, if you cannot find a scheduling command or schedule a role to allocate to a robot through enabling communication or negotiation, we will rely on the last layer, which is centralized. Basically, everyone send information to the central computer, which will do a centralized decision making for the whole fleet. Okay, so this is a scheduling project we did a couple of years ago. The next one is next thing I'm going to talk is about how we detect anomalies in leaf. The first one the first one is related to our the first national robotic initiative program. That time we built a octorotor, which is about wings. I think the dimension is about I would say 3 meter, or no, 2 meter dimension for the drone. So it's pretty big one. We can carry 15 pounds of payload. We anticipate to use a drone to conduct rapid scanning. Dr. Reza, that time he built a spectrometer supposed to be put on the drone, but later on we figure out a spectrometer have very tough requirement. For any robotic platform or UAV platform, it cannot be really close to the plant at that time. So we didn't use a spectrometer, we still use camera. Vision camera to do our job. So in our drone, we have a gimbal there. which will stabilize the sensing platform. We use the orthogonal projection for image processing part. But as you know that, when you're scanning through the field, you will have many, you will find many probably disease or something, right? It's not just one. So if you want to do a real-time tracking of all these things, you have to make sure if detect one or detect five, then when your drone is moving or flying, the next frame, the image is coming, you will be able to associate the correct leaf with correct disease, right? So if your leaf one have a disease one, leaf five have a disease two, the next frame you need to know, oh, disease two is for leaf five, not leaf one or leaf three. Okay, so that's something we call data association. So it's basically another layer of algorithm after your estimation part. Okay, so this picture show you the image threshold detections. This show you overall data association stuff we developed, I think about 2016. So this image threshold detection scheme, it's basically multiple common filter stuff inside. So you have different regions. When you put certain thresholds there, it will detect the pixels and figure out if there's something strange, right? Either disease or nutrient stuff. Okay, and then you use this called multi-target geolocation algorithm, try to correlate your pixel with the target, because all these things need to be related to your UAV or drone motion status, your position, orientation, etc. Okay, then you'll build the probability data association stuff, PDA, for each measurement to target pair, and then you update them, right? So typically in your common filter design, you have propagation step, you have update step, and other things like that. Okay, prediction step finally. Okay, so this algorithm not only just detect a disease or something, it also help you to associate different leaves or different target with your particular phenomenon you see. This picture show you the experiment we did. That time we used this drone I just mentioned. It's about it can carry about 15 pounds. We built from scratch ourselves. We fly in a Barton at the UCF, and then we assume that in the ground, when the UAV is hovering here, UAV find out there's 4 of them, which show the different pixel color, okay, to denote to represent different kind of phenomena you see on the leaf. Okay, so when the UAV is flying, hovering, you can see that the image is not so stable. Sometimes it can detect, sometimes it cannot detect, and all these 4 cross here is basically show you how we associate the leaf with the target. Okay, if you're in this picture show that if your pixel is kind of outside of this circle, it basically we call it, we lose the track, right? We lose track, then the next frame will come and try to correct it. Okay. So this slides basically show you what we have done. If we have multiple target, you need to track, and in real time. Okay, I know in phenotyping or using UAVs, typically people flying drones over the field and get the overall picture of how the field looks like, either use thermal image or spectrometer or camera, and they will get a collective image of the whole field, like yield or disease distribution and other things like that. But this data association algorithm can help you to identify individual one, okay, and associate with them with frame by frame. Okay, so this will be the one of them, and this project. Let me see what this. This project is we try to use common filter to find out if the leaf is healthy or not, okay, in the strawberry field. Many commercial strawberry fields are managed very well. They don't have disease and nutrient stuff, deficiencies. They manage very well. They monitor all the time. But there are some like a field, they maybe lack of people. They're not managed very well. So you can see the leaf kind of dead. Lots of leaf are dead. So at that time, I think I forget which year. So we developed uh, an algorithm for our robot, which go over the strawberry field to figure out the condition of the leaves. Okay, at that time we develop a new color ratio. Use this color ratio to figure out it can be more stable under different light condition. And then we, in order to figure out the leaf status, we first have to detect the leaf. Then we group leaf together because some leaf belongs to this strawberry plant. The other leaf may belongs to a different strawberry plant. So we have to group them together. Then we detect whether or not the leaf is alive or not. Depends on the how green it is, right? If it's like brown or very yellow, we will say it's dead. So this will be the basic how to detect the leaf is alive or not. It's more like static measurement. But in order to reduce the label, and you don't want to carry a sensor or camera there, bend it and try to go through the field just by yourself, right? So you can send robots there. So this control algorithm here for 3 is basically we have a robot carry this stuff, right? So robot will first detect using our color index, and then find the relative pixel measurement from the beginning of the row, and then we do the relative position estimation. Then we can convert the relative position back to the robot localization information. So this video show you. This is our robot moving over the field. So the red dot basically means that the camera is able to detect some plants. You see all these red dots. And on this picture show you our leaf alive or not picture. All the green dots basically show this leaf is healthy, and the red dots show that this leaf probably dead. Okay, so you can see it's autonomous, and it's pretty quick. It will be pretty useful, if you want to check each plant, one by one, and you can count the healthy one. How many of them are healthy, how many of them are dead. So the growers and farmers can do something, right? If you're kind of close to that, probably you can use pesticides or maybe apply for nutrient to help. So that was done a couple of years ago. This project is my collaboration with Dr. Ajhara and also Dr. Shen. We are still working on it. We published a paper together last year in a IEEE conference. So motivation is that we try to develop a sensor which combine vision and electrochemical stuff. Okay, the vision part is do quick scanning to figure out if the a strawberry plant lack of certain nutrient, and that vision part we're almost done. Okay, we initially used not non-AI methods, but since last year we used AI methods. First we used I forget which method we used. We used the mobile net 3 small, and this year we used the EuroV 10, I think, to achieve better results. So what we do is that we collect lots of image. I think thanks to Dr. Ajhara, he sent me lots of picture. We use that to train our neural net model. Among all these pictures, the real picture we have more than close to 800 healthy one, and we have about 650 nitrogen deficiency leaves, and close to 800 phosphorus, I think, K deficiency, and 640 phosphorus deficiency. Okay, and also applied the data augmentation methods in our AI model to increase the number of images we have to train the model. Okay, then we develop a handheld device. We tried this. Actually, this was tried in. I'm not sure. This probably in perhaps patch nearby. We tried also sensor in Dr. Ajhara's experiment field in Gulf Coast last year. The issues with this sensor is that it affected by the sunlight a lot, so we have to use umbrella, okay, to cover the sunlight, so make our detection more accurate. Also, we have to make sure the image kind of in the center, not like in the half or too small, or maybe it's too bright. Okay. That's the image part, vision part of a sensor, and our chemical part is still in the lab. We haven't been able to integrate together into our sensor box yet. But I hope that in the next few months, after the lab experiment is done, we should be able to integrate the chemical part into this sensor box. So that was a nutrient deficiency detection sensor we currently still building. The last one I have today is mechanism. This was my collaboration with Dr. Zhenfei Guan and Dr. Ajihara. This project was done a couple of years ago, maybe 3 years ago, I forget. We developed a new type of end effector. I'll show you later on in a video, what the current end effector look like. The current end effector was built by Dr. Reza from UC Merced. They have some issues, and the one I'm showing you here supposed to be perform better because this is the currently picking success rate vary between 50 to 97%. Mostly the failure is due to the very inaccurate height estimate or depth estimation using vision. Plus, it was causing damage because the picking mechanism they used. So this new end effector we developed several years ago is a scoop pulling type. So it's a spiral motion, and it will cover from the bottom and then pull. They don't have any sharp edge contact with the strawberry. So our success rate in field experiment, we did several times in the nearby strawberry field. We did once in Dr. Ajihara's lab of experiment field a couple of years ago. The success rate is close to 94%, and almost no damage. This experiment we did in the lab show you how the this show you how the camera inside of the end effector are able to track this red stuff. Okay, we use this Lego piece to represent strawberry in the lab. This is the experiment in the field. This robot is picking one, and then the algorithms try to search where the next one is. So I think that's all the project of the past decade, working my lab has. This picture show you the end effector we used in the lab currently. This have gone through many software iteration because we have to make sure the strawberry is in perfect middle of the claw. Otherwise, it's very easy to get pinched and damaged the fruit. Okay, but for this one I mentioned, it doesn't need to. It can once it's spiraling and scoop the strawberry, it will push the strawberry into the middle and not causing any damage. And this was the analysis we did, I think 2 years ago. It's once the strawberry was picked in the field, and after about 24 or 48 hours, how it looks like. So it shows that most strawberry are still fine. It didn't get damaged by this kind of picking. Last year, our picking success rate using this kind of mechanism, the motion control, everything together, I think it's about 70, probably average 75 or 80% good. And most of the damage is caused by the mechanical issue, not I think the number one issue is the height estimation. Number two is mechanical issue. This year, we did several experiments this year. The success rate is lower. I think mostly because we went to the new field. The field geometry is different from previous one. They still have lots of tuning we need to do to enhance the accuracy. But before I end my talk, I really like to thank my collaborators, Dr. Ajihara, Dr. Guan, Dr. Isani, Dr. Karki, and also my colleagues at the UCF here. And two farms, we went to Pappas Patch and Amber Brooks farm. We went there this year. Also, I'd like to thank all the students who have been working in the lab. We have many of them, and we probably have like 20, 30, senior design students, undergrad students, and we have probably 10 graduate students who went through all this project. Finally, all this project funded by NSF and NIFA. We are really thankful they willing to provide support to us. So before I take any question, we can take a question, but in the meantime, I show you what we have done recently probably yesterday in the lab. Let's see. Let's kind of try to pick something and no, let me move faster. We slow it down sometime, we put some kind of cover here because we have the sand is too loose, the wheel so easy get stuck there. So we slow down the motion, increase the torque, and this time works fine. Okay, maybe I can move further. This already moving to the field, and the claw is picking the strawberry. I'm not sure if you can see it. You pick one and drop to the ground. Pick one, drop to the ground. Okay. So I think that's all I have, and I'll be very happy to take some questions.
Okay. Thank you, Dr. Xu. Do we have any questions from the audience? Please feel free to jump in and ask or type. Be glad to read it. Well, while we wait, I do have actually I had some, more technical questions before, but I got so excited with this video of the picker. It's so impressive that I'm curious, what kind of, so you need some kind of force feedback there to do this, right?
You mean when you're picking a strawberry?
Yeah, I mean,
No, we don't have any feedback there. We just design different kind of mechanisms to make sure we do not damage the fruit. And as I mentioned, the height is a big issue, right? We purely based on vision. We have some algorithm developed to like frame by frame to predict the distance between a bottom of strawberry to your claw. So we make sure it doesn't, sometimes when you damage fruits is because you're picking in the middle, you kind of punch into it. So for this kind of claw, we basically make sure, you have a correct height and also make sure you're in the middle of the fruit. For the different end effect I show you guys, that's scooping and pulling. This requirement will be less. We don't need very precise prediction on height and center position.
So here, basically, the main mechanism that is preventing damage is really the mechanical design, the shape of the I guess the gripper. It's not gonna. Okay, that's very impressive. So you said that the success rate is about 75 to 80%?
Yeah, I think last year was about 70, 80. This year is a little bit worse. As I mentioned, we are currently in a new field. The field geometry, the height of the bed is different. So, and also the bed is not very uniform height, causing some issue to our estimation and image processing and picking stuff. Also cause lots of issue to our motion as well, because the field is very, very sandy compared with the previous one. It's pretty firm field.
And the challenge in height estimation is because you need very precise, like maybe millimeter level precision.
Yeah. For this kind of end effector, you need a very precise. I know most of the, I think one of my students right now is working on how to enhance the accuracy of the height. Most of the image AI methods, they can predict very well X, Y direction, but the depth information always have some issue. So this reason we have some kind of feedback control to check the step by step the image size of the fruit, try to predict are you really close or not really close to the target.
And I'm guessing current RGBD cameras don't give you the kind of precision you need in this
You mean
scenario?
RGB and yeah, we have a we initially have a RGB and depth camera as well, but not accurate enough, so it's not very helpful.
Yeah.
Mm.
All right, do we have additional questions?
Yeah, I can ask one. Hello, Dr. Xu.
Hey, how are you?
Thank you for the nice presentation. So, I'm not sure if you have already answered this, but I was just wondering, in one video you showed like how the vehicle is coming out of the row, and when trying to enter the row, it is kind of getting stuck and trying to
Mhm.
hit the strawberry beds. So
Mm.
currently, like, do you have any mechanism to prevent that, or have you something in mind instead of just increasing the torque power or something like that?
Yeah, I think for the sandy terrain, yes, increasing torque power is definitely what we are doing. It help a lot. In terms of how to align perfect with the head, we just initially we kind of let the robot kind of do a turn very close to the row head. Now we leave a little bit more distance, like initially maybe like 10 centimeter. Right now we give like half meter distance, so we can adjust a little bit better before it jump into the next row. So it's not like it's more practical, small fix, which can help.
Okay, thank you. Thank you very much.
Hi, Dr. Su.
Yes.
I am Kalara.
Hey.
Hi. This is really impressive because I am also working on strawberries. I
Yes.
have two practical questions. The first one is, how long does it take to complete harvesting for one row? And the other one is like, especially when the strawberry plants are growing, they become like bushy. So
Mhm.
when the fruits are under the canopy, they still can the machine can still detect them and harvest them.
Oh, that's a good question. That's actually very difficult to solve. First question is the speed. Currently, our mechanism average picking speed is one strawberry need about 6 seconds. That's pretty slow. But you can speed up because currently we have lots of pulse command in our image processing and how the data arm is moving. By the data arm is developed and built by Dr. Isani. So if we streamline or optimize the software and we probably can go down to like maybe 4 seconds per strawberry, still much slower, maybe 4 or 5 seconds per strawberry if we really streamline the software and other things. But I think still slow. So our argument is that we are not trying to compete with human picker, right? They can pick like maybe one strawberry, maybe 2 strawberry per second or something like that. We are trying to what we try to do is that we try to build more and more of them. So that way we probably can speed up, right? In terms of strawberry being fully covered or hidden under the leaf, our robot currently cannot do anything. I know some
Okay.
company, you guys know the company, they have some mechanism we developed. They can kind of open the leaf and see through inside. We cannot at this time. We only pick the one which is shown, which can be seen by the camera. You always can find a different mechanism and try to pick stuff which you can use mechanically, perturb them or doing something. For very interestingly, for many of the U-pick farm, based on my observation, like the one we went to always, most of the strawberry actually can be seen from us because their plant is not very densely planted. But the many commercial, not non-U-pick farm, their plants are very dense. You probably have to find a way to exposure all these fruits to the camera. Otherwise, you probably cannot pick. I know Dr. Arjuhara's field is also have pretty dense leaf, right? If I remember.
Yes.
Yeah.
It depends on the cultivar actually.
Yeah.
Yeah. Thank you so much. Thank you so much for answering my questions and also for this amazing presentation.
Thank you.
Okay, well, thanks everyone for joining us today. Thank you again, Dr. Xu, for a great, very exciting presentation. And well, see you in our next seminar. Thank you.
Okay, thank you guys, and I'm glad to do a presentation here.